So when we estimate abundance, we want to see this number estimated somehow. Our density is 1, phi is 0.5. So let's make, again, a simulated landscape. And now we kind of know how to estimate phi, how we can use this information to take our counts, account for p, and get density or the total abundance right. So we say our time intervals are going to be 1, 2, 3, 4, 5, which is unusual in the real world. So we heard 104 individuals, and we used the data as before to fit this simple removal model. We had 0.5 as the input. We got an estimate of 0.4. So this is how it relates to the data. Again, we binned in 1 minute intervals, true value, what we estimated. And we can calculate p for the max of this vector, so t int, that was our time interval endpoints 1, 2, 3, 4, 5. The max of it is this curve here, where we stopped collecting the data. So that's what we use in this cumulative density function, e to the power minus max duration times phi, which is the exponentiated coefficient from our removal model. So for 5 minutes, that's going to give us 0.87. So now if you think back, we had y equals n times c, which is also density times area times c. And now we say c equals p. That is, we don't deal with any kind of observation process, it's just availability. If we can estimate p, which is here, 0.87, then we can take this relationship and calculate n. So our true abundance that we had in the simulated landscape is 104. So we can take our detections, the number of individuals detected, divided by p, and get 111 instead of 104. So because we know the area, we are lucky. We can also then say true density is n over a. Our estimate is n hat over a, which is 1 and 1.11. So now we can use the best model for Tennessee warbler, but I skipped that. So I can just go back to the end of this HTML and show if you do that for the real data, which begins here. So we had Tennessee warbler, process the data, identify the best model. This is the summary. This is how we calculate p for that area as a function of the best model coefficients, without explaining it too much so that we have some time to play. Then this is the GLM, and we calculated an offset as log of p, because it's on the log scale, and we know y equals n times p. So the log of it becomes mean abundance on the log scale plus log of p. And so if we throw in p as an offset, then we get our intercept, which is now corrected for this availability bias. So we can estimate our density is 1.33 on average for this species. But as we will see on day 3, next Tuesday, this is not quite correct, because there's a lot more that goes into this C. So it is not just P, but P times Q, and what that Q is going to be that is the topic for day 3. Now we have 2 exercises. You can pick what you like more. Open up the Shiny app. For exercise 1, I would say use that bsims her. And why that's different from bsims age is bsims age is using only forest as a habitat. Her means habitat, edge, and road. So there you can incorporate some other strata. And the point here is you can change the behavior based on the stratification, not just, oh, these are the already mated individuals versus not, irrespective of where they live. But if they live in the edge, then they might be more active because that's just where they vocalize more. So you can kind of play with different kinds of mixtures and see how that might affect your estimate of phi at the very end of the tabs. And then exercise 2 would be what I'm going to walk you through as I open up the Shiny app is how to define some edge cases of the simulation you want to compare, and then copy some settings back to R, run a bunch of simulations, and then kind of compare the output. Any questions so far? Because we are done with the statistics part of it, and if you need me to go over the population estimation part a bit more, let me know. Otherwise, I will just open up the Shiny app. And I can still talk and explain things while I'm doing this. So let me know if you have questions. How do I open that? Run app. bsims.
Peter?
Yes?
Would you say that parameterizing and finding the best model for the detection part, would it be more like hypothesis driven or data driven? In the sense that if detection is a nuisance for account for, maybe you just want the best model to account for it to have the best corrections and get more accurate estimates of true abundance, right? So in that sense, you just want the best detection model, not necessarily.
That's a good question. So far, I've mostly used hypothesis-driven models, and so in the sense that you have a good idea about how behavior might change over time or how detectability might change as a function of habitat structure. And I think it makes more sense to focus on those that might make an effect and less so, okay, let's see if climate has an effect, because it's just 40-year average or something. Like, why would you expect that the 40-year average climate data would influence detectability? If there is spatial gradients in it, that might be more to do with greening up or phenology, like vegetation changes across years. So I think you would want to focus on the more proximate cause of what is driving it, and not just finding something that happens to correlate with it, because that just helps you understand and check whether your estimates make sense, right? If it's going down over a season, you kind of expect that. If it's showing the opposite trend and you don't even know what that correlate is related to, then it's going to be harder to troubleshoot your model. And another nice feature of the conditional likelihood is we can have like tree cover driving detectability. And also we can have tree cover driving density. And these two won't get confounded because we condition on the species being there and then estimate detectability as a function of habitat. And habitat is also a very strong predictor of abundance. So if we have them in a joint modeling like admixture or occupancy, that might lead to some problems. And also when you're doing model selection, it's not trivial how to simplify the models. Should I start with simplifying the detectability part or with the abundance? Like, which way should you go? This way, you just simplify one model, use it as an offset, simplify the next one. So this conditioning saves you time and headache.
Yeah. Yeah, I guess the question shouldn't have been dichotomous anyway. I mean, it's always better to be hypothesis driven and have an expectation and then contrast, right? But I was probably thinking more with the mixture part seems to be a little bit more tricky.
Yes. So there is that paper which I didn't cite in the slides, but in 2008 we put together a paper just about removal models, and we looked at sample size requirements and what kind of patterns you see, what kind of biases you get or uncertainty. And it turns out that yes, really the finite mixture is working better when you have lots of data and you can spend that extra degrees of freedom. But it also becomes really uncertain. So in terms of the confidence intervals, it just becomes really wide. So it's kind of a trade-off. So it tends to work better when you really have the data to support it, but oftentimes the probabilities that you get at the end are not going to be super different. Most of it comes down to the uncertainties that are involved. So now I'm showing it like this is the usual landscape. Do some behavior. Let's give them some movement as well. So once we start detecting them, what I want to do here is take this detectability parameter really big. So we detect everything. That's just a way of getting rid of the distance sampling part. Let's detect everything. And then if I go here on the transcribe, I just simplify the distance to 0 to infinity. So we only have one row for the time intervals. And so in this simulation, what we can do is to look at undercounting and overcounting. So you can see here, this is my estimate of phi. I had 0.5, I'm estimating 0.45, not bad. If I pull this slider down, which means there are, what was the number before? So here you can see total is 1 because density of 1 over 100 area units, that is going to be like on average 100 individuals. If I start sliding this up down, then I'm getting 85% as distinct individuals identified by the observer, 86. So this is how many individuals as an observer I perceive. If I move this upwards, that means I treat that 100 individual as 120 because I somehow count the same individual multiple times. And you can see this affects phi. If I'm double counting, the estimate is downwards biased. If I'm undercounting, I get higher estimates for phi because I'm just going to assume the same individual vocalizes more, but really those are events coming from multiple individuals. And so how do we misclassify individuals? What is it that's happening in the background? That's something I can show it to you. Maybe I just go back to R. Oh, I need to stop. So let's say we have perceptibility or perception 75. So we are going to count 25% less individuals. So if you look at the events, then you can classify the locations of where those events are happening based on XY. Oh, sorry about this. I just... Okay. So you can say these are the locations for the events. And if some events happen close to each other, I might say, oh, it's kind of the same individual, or like here, the blue X, or this red something. So if you now look at this dendrogram, come on, RStudio, there. And I say, these are my events at different locations, then I might say, if I cut it down here, I get everything. Like all the events are going to be a distinct individual. If I cut it here, every event is going to belong to the same individual. I just think it's everywhere, it's all the same individual. So depending on where you cut this tree, which is just clustering together the location of these events, you can pretend that you under or over count based on where they are located. And I think this is a plausible mechanism of why you would count individuals twice or not twice. If they move a lot, they might get clustered with other individuals. And so if I go back to Shiny, as I recall, we only did change this to really big and then also used a bit of movement. So this is where we were. We get our estimates for phi and we say undercount. We get this bias. Now, if you want to do simulation, this is just one realization that you can see here. If you go back to the first tab and change random seed, then you're going to see a different outcome, but under the same settings. But when we do simulations, we want to run the same settings multiple times, either because we want multiple landscapes or because we want the same landscape 100 times so that we get a sense of, is this really just happens to be because of the data? So sometimes you get high, sometimes you get low, but on average it's all right. Or you always get higher, right? This is what we want through simulation. Do it many times, 100, 200, sometimes more, and look at the picture across all those runs. So you can go here and copy the settings. You put it back into R. This is one settings. You see perception 0.75. If I go back here and set it to 0.2, now it's 0.2. So if I have these settings, I can copy them and come back to R and say X equals what I copied from there. You can see a function called bSimsAll. And what this X becomes is just like a parrot telling us what our settings were. So by telling bSimsAll, we did really nothing, just captured the settings. What we need to do is call either new. Now it's running the simulation as we saw before. Or if we want more than one of these, we can say replicate twice. And now we have two realizations under the same settings. So now if we run 100, then we are going to get a list. And on each element, we can calculate what is phi, and then compare that to our original 0.5. So this is done here in a slightly different way. You load the package, set some values, how many replicates you want, and then you set values for this perception. We saw what 0.75 did versus 1.2. Those were the two endpoints. That's totally valid to just run the two endpoints, and maybe in between where there is correct identification of the individuals. But you can also not just look at 3 points, but the whole gradient. So what we do here, we create values between 0.5 and 1.5 by 0.1 increments, and we want to run all of this. So this expand list is just going to repeat everything except perception is going to be different. So the first one, 0.5, the next one, 0.6, and so on, up to 1.5. All the rest is staying the same. Then you can call bsims on these settings. So now B1, that refers to these settings with 0.5, and B, so the length is 11. So the last one is 1.5. So these are my settings. Now I can call new or replicate on these. So that's what's happening here. And sorry if I'm running a bit fast and not explaining what lapply means. But if you want just to change the settings, then you can just change the settings and keep everything the same. So for each element of B, it's going to call this function where that element is now called Z. So we can say Z replicate B times and use 4 cores. If you are running on Windows, this might not work out of the box. You need to set up a cluster, but on Unix, this is going to use multiple cores, which means it's going to run faster. So then, once it's done, we are going to then estimate phi, and there's a handy function. So if on a simulation object you call estimate, that is what you can see in those graphics in the Shiny apps. It estimates phi, something called tau, which we are going to talk about next time, and the density. So now if you just look at phi and how that varies, oh, I think this is going to take a lot of time. So what if I just say b equals 3? So once we have our estimates for phi, then I just create some plots to show it how this perception under versus over counting is going to influence our estimates. So if you play with Shiny and get a sense of what kind of influences you are getting and whether that's huge or not, then you can take those endpoints, create a gradient or just a few points in between, and then run more extensive simulations. So that was kind of the idea behind this package, of repeating this many times so that we have a good sense of these biases and the uncertainties involved. Okay.
Would this, sorry, if I may ask, would this
Sure.
be the kind of thing that would be really great to look at and being like, okay, well, we're not really sure if our observers are perfect. We're pretty sure they're not perfect. And so we think that, you know, there's a chance that they're detecting between this and this many, like under and over.
Mm-hmm.
And then you run your models essentially assuming either one of those. And then that gives you an estimate of your abundance by saying, okay, we're fairly confident that our abundance is between this and this based on the
Yes, I think you can look
know.
at it that way, that you would kind of run a sensitivity analysis that
Okay.
it's probably not like outside of this range, but if we assume it's not perfect and within 0.9 and 1.1, then this is kind of the bound within which our estimates might vary. So I think that's a good caveat. But also my question would be, how do I then make sure that I understand what is the real magnitude, like how to design an experiment that would tell you, well, it's not between this and that, but it's exactly like it's more likely to be lower or higher.
Yeah. I guess I was just thinking, because like there's certain errors that like I don't think, no one's going to be perfect. You can't expect your observers to be perfect. We know they're not going to be perfect. So where do we go from there, knowing that the real world is messy.
Right. Yes. No, that's a good point. And I think I'm always thinking like, now I know what's happening. How do I now estimate it from the real data so that I not only know that, oh, this can be a problem, but whether this is a problem or not, or this is going this way or that way, like how do I make that next step? I think this is also helpful. And we are now only having 1 minute. So the last thing I wanted to show is now we have different rows for each of those settings we did between 0.5 and 1.5. And the columns are the replicates. We had 3 because we were short on time, but you could have 100 columns and then you can create a plot. You can see the median of phi is perfect, where there is no deviation from the real number of birds. If you overcount, phi is going down. If you undercount, phi is going up. For probabilities, this is what it looks like. So you get this range of kind of plus minus 3 on the probability scale, which is pretty significant. So if you're in this range of 0.9 and 1.1, it's okay. It's kind of within the range of the uncertainty you would get just by everything working perfectly. But towards this end, you should be more worried. So if you know that, oh, my real numbers are likely in this range, then you might want to take this into account. So thank you very much. This was a probability of availability component of C. Next time we are going to finish with Q and then putting everything together and add more complexity. So thank you very much. If you have questions or want to get some pointers, which eventually I'm going to collect together and just put it in a nice long list, so you will have all those for reference, and also where we put the videos if you happen to miss something or want to rewind, that is going to be shared eventually. Thank you very much and enjoy the rest of your day.